Sample and distributions in the central limit theorem. Here we have a visual of the population distribution that is a normal distribution. First, in A, we have the population. B, we have a sample and distribution of x bar when n equals 2. In C, we have a sample and distribution of x bar when n equals 5. In D, we have a sample and distribution of x bar when n equals 30. If the original population is normal, the sample and distribution of x bar is normal. This is true no matter the sample size. For n equals 1, n equals 2, n equals 5. And notice, as n increases, the spread decreases. Here we have a population distribution in a U-shaped distribution. The population is not normal. When we have a sample and distribution of x bar when n equals 2, it's still not normal. When the sample and distribution of x bar is n equals 5, it's approximately normal. And when the sample and distribution of x bar is n equals 30, it's approximately normal. If the population is U-shaped, the sample and distribution of x bar is approximately normal for fairly small sample sizes. Here, it's n equals 5. And also notice, as n increases, the spread also decreases. Here we have a population distribution in a uniform distribution. A is the population for all values of x. B is a sample and distribution of x bar when n equals 2, is not approximately normal. C is a sample and distribution of x bar when n equals 5. In here, the distribution is approximately normal. In D is a sample and distribution of x bar when n equals 30. In here, it is approximately normal as well. If the population distribution is uniform, the sample and distribution of x bar is approximately normal for fairly small sample sizes. Here it's n equals 5. And again, notice, as n increases, our spread decreases. Here we have a population distribution in a right-skewed distribution. A is the population. B is a sample and distribution of x bar when n equals 2. C is a sample and distribution of x bar when n equals 5. And D is a sample and distribution of x bar when n equals 30. If the population is right-skewed, the sample and distribution is also right-skewed for small sample sizes. The sample and distribution becomes more and more approximately normal as the sample size gets larger. N is greater than or equal to 30. So for A, B, and C, it's not approximately normal, but D, it's approximately normal. The central limit theorem. No matter how the original population is distributed, as the sample size increases, the sample and distribution of x bar becomes closer to a normal distribution. Usually n equals 30 is enough to get a sample and distribution that is approximately normal, but it will depend on how skewed the original population is. These results hold even if you don't know how the original population is distributed. So even if we don't know anything about the original population distribution, the sample and distribution of x bar will still be approximately normal as long as our sample size is large enough. This allows us to do inferential statistics even if we don't know anything about the original population. And this is an amazing result.